Hi, and welcome to this new episode of Swift Community. So this time I have Donny Wals with me. Welcome, Donny.
Hey, Vincent, how are you?
Very fine, and you?
I'm doing fine too, thanks.
Perfect. So thanks a lot for joining, and you're going to tell us today about how we can use generic to kind of structure and make our code more reusable in Swift.
Absolutely, yes. So this is all based on a little post that I wrote a while ago that's all about using generics and protocols to build flexible components. Since generics is obviously a topic that a lot of people are confused by or not sure like what's it good for or how it works. So the whole purpose of the post that I wrote was to write this object, a cache-backed data store, I called it. We can see it in the playground.
Yes.
That either takes something locally or something from a remote. And depending on whether the data exists or not, like the cache-backed data store would do everything. But the sort of the API that I had in mind is on the screen right now. So as you can see this, you could probably program this without any protocols or generics if you wanted. However, that wouldn't be very flexible because then our cache-backed data store would probably look a little bit like this, where we could say class cache-backed data store, and then maybe it would like have a local store, data store, and its type would be what? Would probably be user data store.
Yes.
So as you can already see, this is not flexible. Like I would be able to write this, but I would not be able to use this same cache-backed data store for something else other than users.
Yes.
So to name this properly, I would have to call this user or cache-backed user data store or whatever. And any data store that I built would probably be built on the same principles and ideas, which I don't know about you, Vincent, but I would say that's pretty cumbersome to write the same code for every single type of data that we want to store. Like I want to be able
that
to
would be
users
yes,
in here.
a lot of code duplication. Yes. And I guess the nice thing is that we have type safety, but we don't want to have type safety at the cost of a lot of code duplication.
Exactly. So what we can do is we can use some protocols and some generics to build this cache-backed data store where we don't have to use a user data store, and instead we can just use any kind of local store with type safety and everything that Swift has to offer. But before we do, let's talk about generics a little bit, because if somebody sees a function like this, well, let's just say func fetch t, and then we use some sort of a key. A key is going to be a string, and it returns an object of type t. Now, this is something that when I first saw it, I remember I was like, what is t? And then you're like, let's click on T, and it's like no quick help. This could, of course, either be Xcode, or it could be because it's a generic. It is the latter. In this case, this is not Xcode's fault, because T is nothing, or rather it's something, it's anything.
We could say basically T is some kind of placeholder.
Yes, and it's not like any, right? Because any can be anything, and T can also be anything, but it's type safe.
Yeah, basically we could say like any can be anything, and T can be anything, but just one thing, you know.
Yes, exactly.
It's like either T is a string or T is an int, but T cannot be both, whereas any, it can be both.
Yes, exactly. That's well said. So if you're like, when is this ever used in Swift? Well, for example, arrays.
Yes.
Right? Now you can say ints equals 1, 2, 3. Now the type of ints here is an array of int. Now we can write an array of int like this, which is very convenient. However, we can also write array of integers like this. Say array int. And this int right here takes the place of t, because an array, as it could be defined, I obviously don't know. I never look at the Swift source code, but it might look a bit like this.
Yeah, that's the general idea. And
right?
we can see that this T, you know, it kind of acts like some kind of argument, but for the type.
Exactly, yeah. And so what we could do is we could implement our own, by the way, this compiler error that I just quickly got out of the way. The reason is that this right here is an array literal, and for some reason we cannot use that to create array int. So what would totally work fine is if we would say maybe array int, and then initialize it with this
The content
array
of
literal.
the literal array.
Right, because this is an array literal, and that doesn't just work. So see, well, let's not go and work through all the compiler errors. There is a way to get this to compile. int123 and array int are definitely both arrays of integers. Do you agree with me there, Vincent?
Yeah.
Cool. Okay, so if we look at this struct of array with t, like, so how does that t thing work? Well, we could say, let's write our little function on array and say object at index int, and that would return an object of type t. And let's also say that I'm going to put here a little nested array. Oh, I know why we had the compiler error. I redefined array. I should not have done that. So we have for our objects, and that is going to be an array of type t. So I've just defined my own little myArray object that will create an array of type t, just Swift's array, not my redefined one. And we have a function object at index that's going to return something of type t. And we're just going to implement that like this. Right, it's going to return objects, which is this array, and whatever index we ask. Of course, this is a very useless wrapper, but it does a good job of showing you what generics are. Because now,
yeah, we can understand, like, we declare a generic, you know, like next to the name of the type, and then we can use it inside the type. We can use it so as the return type of a function or method, as an argument, or to specialize a property that is in itself a generic type.
Exactly, yes. So as you were saying that, I went ahead and I created two instances of my array, one that holds strings, one holds integers. So I would say strings.object at 0 or int.object at 0. If we run this, you'll see that in one case, I get a string printed, and in the other case, I get an integer printed. So we were able to write a single struct that was generic over some type t, and then we could work with it, and t is strongly typed. So t can be anything. We can put whatever we want for t, but once we set t, we know that it's always going to have the same return type. So in this case, it's always going to be a string, and in this case, t is always going to be an int.
Yeah, and also what we can maybe mention is that, so as you said, once we have provided a type for the generic argument, we get a new type that is set. So it means that the variable strings is of type myArray of string, int is of type myArray of int. And if we try to affect the content of int to the variable strings, we'll get an error because the compiler will be able to say this is not the same type.
Yes, exactly. So to demonstrate that, we could say append an item, and that takes an item of type t. It's not going to return anything, and all it will do is just objects append item, right? Simple enough. So what we can do now, because self is immutable, let's not fight the system and make this a class then. So one thing I cannot do is add something that's not of the same type. So let me quickly add this initializer here. There we go. So I cannot say strings.append1. That's not going to work. I can say strings.append string. Right, this will not compile because there you go. Int cannot be converted to string because we told that this generic t here for strings is going to be a string. Okay, so let's bring this back to our task at hand, which is building this cache-backed data store. Now we can already try and define it a little bit. We can say cache-backed data store, and it's going to store something. We're not entirely sure what, but it's going to be anything, almost like an array or dictionary or other container type in Swift. So we're just going to say t, or we can use a different identifier instead of t, which is more readable, and we're going to call it stored type. That's all we'll do for now, right? So this cache-backed data store now has a generic argument called stored type. Store type, of course, does not exist. It's the same as T, except this you can understand when you see it, and T is somewhat generic even for a generic argument. So what we're going to want to do here is I'm just going to define two little placeholders. I'm going to say I want to have a local store, and I'm going to use a protocol for that. So I'm going to do protocol local store, and I want to have a remote store. So I'm going to say remote store, and that's going to be of type remote store. Pretty straightforward here. That we don't have any initializers, it cannot find local and remote store. So let's fix that before we move on with this example. But this looks good, right? Sort of a good starting point.
Yeah, and it also gives us like kind of, an outline of the internal working of the class. We can see there is going to be a local store. We're going probably to try and hit this store. If there is a return, we return it. If there is nothing in the local store, we use the remote store, and then we cache the value locally.
Exactly, yes. So let's get started by saying I want to have a protocol local store, and I want the local store to have two functions, because just like you said, we either want to retrieve something from the local store or we want to write something to the local store to cache it. So we're going to say function fetch, and then, well, let's just assume that every object that we put in the local store is going to have a string identifier. We're not going to constrain that in code, but let's just assume that that will always be the case. And now we have to return something. I don't want to type user. I cannot type stored object or stored type.
Yeah, because it doesn't exist for the moment.
Exactly. Luckily, we have a way to bring generics into local store. And the way we can do that is through something called an associated type. So I can say associated type, stored type. And what this tells the Swift compiler is that this local store protocol must define what stored type is. It's almost like a generic. So when we define our user data store, in this case, we are going to have to tell Swift what stored type is. We can either do this explicitly with a type alias or through type inference, where we just implement fetch identifier, and Swift will know that whatever the return type for that function is will be the return type, or will be the type of stored type.
So in a way, maybe if we wanted to say it like in more like with just English word, we could say that this associated type, it's like we are promising the compiler that whenever we want to use local store, we will indeed provide a type that the compiler will be able to use at compile time.
Exactly. By the time we compile our code, all will be clear. That's essentially what we're telling the compiler. Don't worry about it. By the time you need it, it'll be there. Trust us. Because us humans are very trustworthy to a compiler. So the second method was func persist, we'll call it. And so the thing we're going to persist is one of these stored types. So it's a persist item store type. And that doesn't return anything. We'll just assume that that's a synchronous operation that will always succeed. We're not going to handle any errors or whatever. And then we have our second protocol, remote store. And that's pretty much the exact same thing. So we're going to have associated type, stored type, because the remote store also has to store something. Next, the remote store, as you might expect, will be asynchronous. So we're going to say identifier string. That will be the ID that we fetch, and a completion handler. And that completion handler will take what will make it? Let's just make it store type optional.
To keep things simple.
Return nothing. Exactly. Normally, you might want to use something like a result or whatever. But let's not go into that. And of course, this is also going to be optional, by the way, because if the object is not stored, no value. Exactly. Okay, so that looks great. And what I want to do now is define our cashback data store. So let's copy this, put it over here, and comment it. And now this looks great, doesn't it?
Yes. It feels like we just need to, like give the actual type for both associated types, and then we're going to be done with it.
Yes. So how would we do this? Well, in with arrays, we could do this. So can we do something like that? Unfortunately, we cannot. We cannot specialize non-generic type local store. Because like I said, a protocol with an associated type is like a generic, but it's not quite a generic. Okay, so what do we have to do now? Well, let's just jump straight into the fix. So what you can do is you can say, I want to have a generic on an object. So in this case, let's make that called local. It will be our local store. And you can say that a generic has to conform to a certain type. For example, in a set, right? A set can hold any kind of value, but only if the value is hashable. So set has a generic argument constrained to hashable.
Yes,
In
and
this
that's what
case,
Swift calls a generic constraint. I think that's the right term, right?
Yep. Yes, exactly. It actually says here, protocol remote store can only be used as a generic constraint because it has self or associated type requirements. And we definitely have our associated type requirement here. So I'm going to say this cashback data store is going to have a generic local, which should be a local store. So we're going to say local is constrained to local store. And we're also going to say we have a remote. And remote is going to be constrained to remote store. So instead of using the protocol types here, we're going to use the generic types here. There we go. We're going to add we're going to make it a struct. We don't need anything mutating anyway. So, okay, this is pretty cool. And we could probably implement our fetch method now. So fetch identifier, and that's going to be a string. And it's going to return, okay, we need more generics. Now, what's convenient here is that this associated type from local store, we can actually access that. So I can say I want to return local dot stored type. So I want to return from fetch whatever I put in my local store. And this is where the fun starts, right? You can see how it's getting more and more complicated, but also very flexible.
Rolling into pieces also, like.
Yes. And also we want this to take a completion handler, because if we fetch from the remote, this is going to be asynchronous. So we're going to say completion. It is going to be escaping. And instead of returning local store type, we're going to pass it to our completion handler. Okay, so now we can write the implementation here. You can say if let object equals local store dot fetch identifier, call the completion handler with the object. Else, we want remote store dot fetch identifier to pass it a completion handler, because we want to say local store persist the object, and also completion with the object. So now it's interesting. Closure expression unused. Is that true? Ah, yes.
I think it's the yeah.
Yeah, I made it half trailing, half not trailing. Okay, so now we have another error, and it says cannot convert value of type remote.storeType, optional, to expected argument type local.storeType. And that makes sense, because nowhere do we guarantee the compiler that whatever we have locally matches what we want to fetch from the remote.
Indeed. And actually, when you started to write the signature of the fetch function, you chose to use local, but you could have used remote. So it was a choice.
Yeah.
Maybe it was a hint that something like, was still not completely like screwed together.
Yeah. So let's replace this with remote.storeType. We just moved the compiler error around. We still have a failure. However, what we can do is we can tell the compiler that we're only building a valid cache if our remote provider fetches objects of the same type as the type we want to store locally. So we can say where local.storeType is equal to remote.storeType. And now the Swift compiler will say, okay, I know this object that you fetch is always going to be the same. So now we only have a failure because we didn't unwrap the object. So let's make let unwrapped object equals object. Because of course persist does not take an optional, persist takes a concrete type. And let's use unwrapped object. There we go. That is the implementation for our cashback data store.
Cool. So as we can see, yes.
What I think is
simple.
It is. And what I think is the coolest about all this is that we have a working program and I have not implemented any of the stores.
So it shows us first that, the both of them, they are completely like decoupled, because if they were tightly coupled together, the code wouldn't be building right now.
Exactly, yes. So this shows you that I can now implement any kind of store, and I can plug it into the cashback data store as long as local and remote have the same kind of data.
Yes, and this pattern, of using where to make two generic constraints match together, it's a pattern we see a lot. For instance, we could imagine like to have maybe like views that accept a model and a provider that provides a model, and in the same way, using a where clause, we would say, okay, this only works if the model provided is the same than the model expected by the view.
Yes, exactly, yes. So you could even make this a concrete type, for example. You could also say, well, this will only work if local.store type equals a string, right? Or string representable, I think actually a string protocol, but you can constrain it to many different kinds of things. And it's like, just to quickly show like how flexible this is, let's define a user data store, which will implement local store. It will have this fetch function, and we're just going to return nil, just because I want this to be quick.
Just to build.
Exactly. And I'm going to implement a struct user here. I'm just going to define it. I'm going to say that store type here will be user, and persist. We'll just do nothing. And we can also implement a class remote store, remote users. And that's
so we could imagine, for instance, maybe user data store, the local store, it could like use user default, and the remote store just URL session to make to call an API endpoint.
Exactly, yes. So now we have our user data store, right? Local, remote, conform to both the protocols. And now let's make an instance of this cashback data store. Local is going to be an instance of user data store. Remote is going to be an instance of remote users. Cash-backed is going to be an instance of cash-backed data store. And we're just going to pass, we don't have to specialize the generic argument. Swift can infer all of this for us. And there we go. We have a cashback data store for our users. Now you can imagine that I could just go ahead and copy and paste this. Just define a different type. Let's store videos. Videos data store, remote videos. And that'll return a struct of type video. Again, it's all just going to be empty because it doesn't matter much for what we're trying to look at here. So we're going to have video data store, remote videos, use local 2 and remote 2. Oh, wait, I should actually have not done that. Yep. And now we can create this second cashback store. If I did everything right, it should compile. And we need cashback 2. So what's interesting that we have now is we have a cashbacked, and if we look at autocomplete here for the fetch, you can see that it returns a user, right? Because that is what we use to build this first cache. If we do cashback 2 that fetch, you can see that it is still a user because I didn't change this type yet. No completions.
Oh, it's on persist.
Yeah. So I had one mistake still in the persist
But the nice
method.
part is that the compiler, found this mistake. It's not a crash that happened at runtime.
Exactly.
So this is a good thing, actually.
Absolutely, yes. So when we call fetch on a cashback 2, we can see that it's video right here. So let's pull these two initializers closers together just to show you but they're basically the same. It's pretty cool, right? The same object, just depending on what stores we pass to it, it will give us different output.
Yeah, and this way, so we've been able to separate the logic of orchestrating a local and a remote store from the actual implementation of the stores, because of course a user is probably going to be a simple object. You don't store it the same way than a video that might be much bigger. Maybe there is DRMs, all these business specific requirements for this particular type.
Exactly, yes. So you can, well, you can do your implementations exactly as needed, depending on the object and the needs. And no matter what you end up with, this tiny little struct here, it'll handle all of it. It'll just take whatever stores you pass it and only apply the logic that if it exists locally, it's going to give you that. If it doesn't exist locally, it's going to fetch it from a remote and tell the local store to cache it and to give it back to you from the remote directly.
And even we could say that as kind of an added bonus, since everything is uncoupled, to test this piece of code, it's also very easy because we just need to make some mock store, inject them, and this way we can test the logic completely isolated from the rest of the application. So basically we get some kind of dependency injection for free.
Exactly, yes. This is exactly dependency management. So we could easily have a test where you implement nil for this and then maybe say our user is an optional user on this user data store, and then just what we call persist, we're just going to say user.item or just self.user equals item. And here in the remote, we can just say we're going to call completion with an instance of user. And that's it. Now we can do a test here on or maybe also add a little print here. Just say print remote fetch print persist.
And do we need to implement fetch also?
No, so all I did was just fill in the blanks for the user data store, local and remote that we had before. So I just added a user here.
So basically it's a very simple cache where there is only one variable, so we can have one value in cache, and as soon as a new value comes in, the old value gets out.
Yep. Yeah. So these two objects are literally what I would probably use to test my cacheback data store. And so what I can do now is say cacheback.fetch, and I'm going to pass it just one as an identifier. And then in completion, user n. So before I run this, I'll tell you what I expect to happen. I expect that we first see a print, which is going to be fetch, right? Because we're going to attempt to get it from the local store. That will return nil. So I expect after that to have remote fetch printed. And then lastly, I expect persist to be printed. And then I expect user fetched to be printed. So let's see. There we go. Fetch, remote fetch, persist, user fetched. Right, so by decoupling it, by making it generic, by making it so flexible, we literally could write a test for this in 1 or 2 minutes.
Yeah, I mean, we would just remove, change the print with some kind of assert also on the result to just make sure that they work as expected. And yeah, we would be able to write our test very quickly.
Exactly.
So yeah, I think it really shows generics are powerful they are in Swift, because we've started with something that might seem, if someone tells you as a business requirement, you need to implement a generic mechanism to deal with cache on iOS, it could be whoa, that's going to be very hard. But we have been able to make a minimal working version, some kind of MVP, actually in a pretty simple way. And that's all thanks to this generic mechanism that you've just showed us.
Exactly, and it uses all the powerful features of generic, just generics themselves, generic constraints, and associated types. So it's got it all, just in this bit of code here. It's got everything. So yeah, I really like generics. I use them a lot. They allow me to program extremely complicated and abstract things without too much code repetition. So yeah, it's definitely something I would recommend people learn. I also would not recommend to dive in as you're just starting to learn Swift, because this is not easy to understand. But if you find yourself comfortable with the basics of Swift, I think this is a good candidate to start learning.
it's definitely like a good way to level up your skill set in Swift to deal with generics.
Absolutely.
Okay, well, I think we've covered quite a lot of ground. Well, I just have to thank you again, Donny, for coming on the show and giving us this really great explanation on generics. So we've shown a lot of code, and of course, if you want to use it, we will put all the links in the description with your original article and a link to this playground.
Yep.
So you know how it is. If you've enjoyed the video, you can give a like. If you have anything or any kind of feedback to give us, well, please say it in the comment. You can subscribe for future content. And well, thank you for watching.
Thanks, everybody. Thanks for having me, Vincent. It's been a blast.
It was a pleasure.
See you around.
See you.